Hello and welcome to the first video of a sporadic series where I'm going to be messing about with MIDI. Now, some of you may not be familiar with what MIDI is, and it stands for Musical Instrument Digital Interface, and you may be aware of it as some sort of music format from decades ago. And you'd be right, but what's interesting about MIDI is it doesn't transmit audio at all. There is no sort of waveforms or samples sent via the MIDI protocol. Instead, MIDI is a sequence of timing events that can be supplied to musical instruments and equipment as and when necessary. I think the original creators of the MIDI specification were exceptionally clever and very forward-thinking, and as a result the MIDI format has really stood the test of time. So much so that it can be modified with ease to accommodate new developments in the industry, and it has also become ubiquitous across the industry. It fully satisfies the needs of making sure that musical instruments and equipment can talk to each other in a sensible way. Now, if you're not interested in music, that's fair enough. MIDI can also be used as a general purpose timing protocol, and maybe I'll talk about that a little bit later on. But from a programming perspective, I think that the MIDI file protocol is quite interesting, and I wanted to explore it in a video. So let's bust out our synthesizers and bags full of cables, and let's get started. And I thought we'd start with a very brief MIDI primer. Here I have some sort of digital instrument. It could be a synthesizer, but these days it could really be anything at all. And in principle, the user presses the keys on the keyboard and it emits some sort of sound that we can hear. But unlike an actual instrument, it's completely synthetic. The keys are electronic switches, which switch something on or off, and accordingly a sound is produced. Now, because it's digital, we don't need to rely on the clumsiness of a human hand to press these switches. We can of course send an electronic signal instead. So we could send something like an on-off event for a particular key. Has the key been pressed or has it been released? We need to identify the key, so that could be a particular note. And there may be other parameters that we want to send too, such as how hard did we press the key. This is called velocity. And these additional parameters allow all sorts of expression in the musical playing. We can package up all of this information as some sort of event and send it to the instrument. Now, as the name implies, this event only does one thing. But of course, for a musical piece you want to do lots of things, so it's likely we're going to want to send a sequence of events. But it's no good just smashing out these events as fast as we possibly can, or else the entire song will be played, well, instantaneously, and it wouldn't sound very good. And as music is a temporal medium, it's important that we include timing information into these events. So let's say at the beginning of the song I want to press this particular note, but I only want to hold it down for a certain amount of time, maybe 100 milliseconds or so. Therefore, I augment the packet with the information to say that this event is occurring 100 milliseconds after the previous event, and subsequently we might want this event to happen 50 milliseconds after the previous event. In effect, we send the delta times between our events. And sending the delta time is quite an important thing, because what if we wanted two events to occur simultaneously? Well, we just specify a delta time of 0. So even though these events have been transmitted in series, whatever is receiving these events at the other end can accumulate them based on their delta times and perform them simultaneously. Now, on the actual hardware itself, it doesn't work quite like that. It's very difficult to do variable numbers of things simultaneously in electronics hardware, but the principle is that you run your electronics hardware far faster than you're sending these events. So these are, let's say we're operating in milliseconds here, the processor on our digital instrument could be quite happily operating in nanoseconds. And so the end result is that it feels like these are happening at precisely the same time. It's imperceptible to us rather boring and limited human beings. And that introduces two interesting properties of the MIDI format. Firstly, it only has to be sufficient for the bounds of human perception. But secondly, it is undeniably real time. And we'll see as we're exploring the MIDI format that where possible, keeping things synchronized and quick takes a priority. Now, as well as being a programming nerd, I'm also a bit of an audio nerd, and I have quite a sophisticated setup for dabbling about with home audio. I don't consider myself a skilled musician by any means, but I like to think that I am, and I try and play my best. And whenever you start working with audio, one of the primary concerns you have is latency. In my experience, when I'm clumsily hammering my keyboard with my fists, I start to notice that I can become out of sync if there's a latency greater than 30 milliseconds. And that doesn't seem like a lot. But it does demonstrate how good the brain is at trying to synchronize audio to real-time actions within your body. It actually becomes very difficult to play anything as the latency gets quite large. And even though I'm not that good on a keyboard, I am actually quite okay with a guitar. And a guitar is typically quite a fast instrument to play. And when I've dabbled with real-time audio effects in the past, one of the things I noticed is that plucking a note on the guitar, I could only tolerate a far lower latency, had to be about 15 milliseconds before hearing the sound, or else my fingers would become out of sync with what my brain thinks they're doing. There are numerous sources of latency in an audio setup, but as you go towards the higher end, that latency tries to reduce. But where is this latency coming from? Well, first of all, physics. You can't have zero latency in any kind of system. But originally, when digital audio workstations were starting to be developed and started to be available to the consumer, the latency was in the cables and the connections between the pieces of equipment. You could only transmit digital signals at low speeds. Throw into the mix the latency of converting those signals from digital to analog, and then at the time some rudimentary effects processing, and eventually you end up by pressing a key and a little bit later on only hearing the final processed sound. Interestingly, as we've progressed with the technology, the communications bandwidth has got much faster. We've got things like USB 2 and USB 3 now, but at the same time we're demanding a lot more from our CPUs to produce more interesting effects and more realistic sounds. The one thing we have going for us in audio is that we're still talking about milliseconds here, and to a computer, a millisecond is an eternity. Anyway, I'm getting sidetracked. Let's get back to the MIDI video. There are several layers to a MIDI sequence. At the most bottom layer is the concept of a channel, where each MIDI event is associated with issuing information to a certain channel, and that channel typically reflects a specific instrument. And it's usually down to your studio setup or dedicated MIDI processors to make sure that these events are sent to the appropriate destinations. In a MIDI message, you can have up to 16 channels, which doesn't seem like very many. But this is where the second layer comes in, the concept of tracks. Tracks are sequences of MIDI events that are occurring in parallel. And here in this new track, some of these events may be mapped onto the same channels that we already have up here. But other events can be mapped to, well, new channels. So we can quickly build up quite a large library of virtual instruments. Before we go and dissect the MIDI file format for ourselves, I thought it would be useful to actually look at a MIDI file. And I found this piece of software. It's free to download, but they encourage a donation. Simply called MIDI Editor by Marcus Schwenk. It's very nice. It's very simple. But it allows us to analyse the tracks and the channels and the messages in some detail. And it's typical of MIDI editors to look a bit like this. In the y-axis of this frame, we've got which particular note on the keyboard is being played. Now, there are always keyboards, even if the instrument doesn't have a keyboard, say it's a drum kit. Of course, the drums can't play notes, but you could assign different types of drum to different keys. In this editor, the tracks are all overlaid on top of each other, and they're all different colours. Here I've isolated track 1, and I'll click on this big event in the middle. And you probably heard it just made a sound. The nice thing about this editor is it allows us to analyse the event in information that might be relevant to a programmer. So we can see we've got this on tick and off tick. That's the delta time from the previous event. It's actually visualised here in what is called wall time. So this is real time, but the event itself will only contain the delta to the previous event. It tells us that it's playing note 77 and it's using a velocity of 100, so really hit that key hard. And the channel it's associated with is channel 0. Now, don't forget, MIDI doesn't contain any audio information. It's simply a way of routing these event packets around a system. So channel 0 needs to be associated with something that produces sound. And in this case, channel 0 has been mapped onto string ensemble 1. In fact, we can have a listen.
These instruments on the side are virtual instruments provided by my Windows operating system. They sound a little bit flat and old-fashioned. Typical MIDI sounds, if you're familiar with those. And that's because on Windows you get this Microsoft GS Wavetable Synth, which is a basic selection of virtual instruments. And in fact I can change the channel to something else, so let's emulate a piano sound instead. One of the nice things about events in time and pitches is they can be visualized on a 2D graph like this. And so I think that's what we'll aim for first. We'll try reading in a MIDI file and visualizing it. And I just love watching the complexity of things like this. But when it all comes together, it produces something rather special. I like it a lot. As with anything that is considered a standard, somewhere there exists a specification for that standard, and this is the MIDI specification official website. And it contains lots of information about how we can interpret what's going on inside a file. Files are a little bit different to just regular MIDI streams between instruments, as they contain additional information that the instruments simply don't care about. Regardless, there's nothing we'll see in my code today that we can't find listed somewhere on the specification website. Now, as usual, I'll be using the OLC Pixel Game Engine for the visualization. Quite a high definition one this time at 1280 by 960 in 1:1 screen pixels. However, interpreting the MIDI file we're going to be doing from scratch, so it doesn't require the Pixel Game Engine to understand how the MIDI file format works. So we'll be coming back to all that later on. Because I want to develop a class that I can use in subsequent projects, I'm going to create a simple MIDI file class. And I'll give it a constructor, and all of the work is going to happen in a function called parseFile, which takes in a path to that particular MIDI file. So just for convenience, I'll add in an additional constructor, which can take in the path and just call the parseFile function. Now I'm going to treat the MIDI file as a stream, because in effect, MIDI messages are sent as a stream. You don't really know what's going to happen next, and so maybe by constraining ourselves to work with a file stream, we'll produce better code for working with MIDI streams in the future. So I'm just going to create a standard input file stream object, open the file in binary mode, and if there's a problem, I'm going to return false.
The first curiosity when it comes to MIDI is understanding how to read values from the file. MIDI was developed way back when, literally billions of years ago, when processors used a different byte order to store numbers than what we're familiar with on our modern desktop computers. So every time we read, say, a 4-byte integer, we need to swap all of the bytes around.
So I'm going to create some little lambda functions to do just that. I've got one here called swap32. It takes in an unsigned integer. Now that will be a different byte order than what we actually want. So the contents of the lambda function simply swaps all of the bytes over. I'm also going to create one for 16-bit numbers too.
As I mentioned before, MIDI files contain lots of additional information that the instruments don't care about, but perhaps the editing system for that file does. So they can contain things like strings.
Fortunately, strings in the file are going to be stored sequentially, and we'll know the length of the string in advance. So I'll create a little lambda function readString which takes in that length and allows access to the input file stream and just successively reads the characters and appends them to a standard string object.
Now we get to the second curiosity with MIDI files. Most MIDI files will never contain information that requires more than 7 bits to store. And that might seem like an unusual design choice for platforms which routinely work with 8 bits. But in some way it does make sense. Firstly, you want to minimize the amount of bandwidth you're going to transmit, as hopefully this will reduce the latency. But also 127 in terms of musical equipment is quite a lot of different things. For example, if you had a keyboard with 127 keys on it, that's going to be quite some keyboard. Alternatively, if you want some sort of expressionistic tool included in your MIDI event, well, 127 levels of differentiation within that expression is quite finite and high resolution. So this comes back to that human perception and real-time thing we were talking about earlier. It's good enough to get by. But limiting yourself to 7 bits does start to raise some interesting problems with the file format. So what if we wanted to, for example, read in a 16-bit number or a 32-bit number? There are on several occasions situations where 127s isn't enough, specifically the timing, the delta time between the events. That could be many thousands of ticks, clock cycles, milliseconds, whatever we want to call it. And so we can't store that in just 7 bits alone. And this is where I think the creators of MIDI did something rather clever. They have a variable length numerical type.
And so when I know that I'm going to need to read one of these types, I'm going to create yet another little utility helper lambda function. As mentioned, the bulk of MIDI information can be represented in this bottom 7 bits. But it's convenient for computer systems to read 8 bits. This means we have a bit here that doesn't really do anything. Well, what if we used this bit to signal to the parsing system that the value we're trying to read in is in fact greater than 7 bits? And that we need to read another byte in order to read the full value. So when we're reading a value, if that bit is set to 1, we now need to read another byte. Again, only the bottom 7 bits are interesting to us. But we can now construct a 14-bit word out of these 2 successive 7-bit reads. Now, what do you think happens if the next byte that we read also had its most significant bit set to 1? Well, the process repeats itself. We read in another byte, take the bottom 7 bits, and form a 21-bit word. And we can keep doing this until we see that the most significant bit of the last byte we've just read isn't 1. And that tells us we've got our complete word. Now, 7, 14 and 21 bits seem like unusual numbers, so I'm just going to stuff all of those into a 32-bit word. Now this may seem like a very rudimentary compression, but it works very well. When we've got low value numbers, we only need to transmit a fewer number of bytes. Great for a system where transmitting things increases latency. I'll store my accumulated value in this variable nValue, but I'm going to need a little helper variable which represents 1 byte. When instructed to read a value, the first thing I'm going to do is read 1 byte from the stream. Now that byte could be completely sufficient to give us the final value, so I'll read that into the nValue variable. But I need to check the most significant bit of this byte, because if it's set, then I need to keep reading. So I will take the bottom 7 bits of the byte that I've just read, and then proceed to continuously read bytes until I read one where the most significant bit isn't set. So in this loop, I'll read the byte, and I'll take my currently existing value and shift it all along by 7 bits, and OR into that value the new bottom 7 bits I've just read. Don't forget to return the final value from the lambda function. Now we're ready to parse the MIDI file. For convenience, I'm going to add in 2 temporary variables, a 32-bit and a 16-bit unsigned integer. MIDI files begin with a MIDI header, and this header contains information about how to read the rest of the file. The first thing I'm going to read in is the file ID. Now if I open a MIDI file in a binary editor, the file ID is always this MTHD. It isn't actually a number that means anything, it's just 4 bytes that can be instantly recognised as a MIDI file. Once I've read it in, I'm going to swap the bytes around and then immediately forget about it, because I don't care. The next 4 bytes represent the length of the header, and today I don't care about that either. The next 2 bytes tell us things about the format of the MIDI file, and getting embarrassing, again, I don't really care about that. What I do care about though is this next one, which is the number of track chunks, and we'll come back to that in a minute because we've almost finished reading the header. There's finally another 2 bytes to read, which ultimately I don't care about. So out of all of that header, all I'm really interested in is this value here. Track chunks is the number of MIDI tracks this file contains, and those MIDI tracks will contain the MIDI events. Notice we've not mentioned anything about channels here. That's included in the MIDI event itself, but as we'll see, there are ways to sort of augment what's happening in the MIDI ecosystem of whatever software is interpreting the MIDI file. The MIDI header is a fixed size, so as soon as we've finished reading precisely that amount of information, we're into reading the data itself. And we'll start by reading the track data. I know how many tracks there's going to be, that's my track chunks, so I'm going to create a loop which goes through all of the tracks. And just for convenience, I'm going to output to the console that this is a new track. If you didn't know, you can still output to the console in the Pixel game engine. That's why there's 2 windows that appear. Tracks themselves also have some track header information. 2 32-bit values, one which identifies the track ID, and if we go back to our binary MIDI, we can see that here. Again, it's just a text string that identifies I am a MIDI track. And the next value is how many bytes are contained within that track. Now, if you parse your MIDI file properly, you're not going to need that value either, because from now on, everything that we read is going to be a MIDI event. And all MIDI events are deterministic in size and content. I guess you could use the track length to check for corruption in your MIDI file, but it also allows you to completely skip reading a track. If you wanted to just skip the next n track length bytes, you could get to the next track. However, we're not interested in doing that. There is one particular MIDI event which signifies the end of a track. So I'll create a Boolean flag just to keep track of whether that's happened. And then I will sit in a loop, making sure that we don't prematurely reach the end of the file, but also keeping an eye out for that event to occur, where now we're going to read in and process the MIDI messages. I'll start by assuming that all MIDI events contain a time delta value and a status value. The status value will tell us what type of event it is. You'll notice, however, there's a little asterisk next to the status byte, because we'll see later on that not all MIDI events do include a status byte. But let's keep it simple for now. So the first information is always going to be the delta time from the previous event for this particular track. And that's going to be one of these variable length values. So I'll call our lambda function to read that in. And then I'm going to read in the status value of the MIDI message. Now, there's lots of different types of MIDI message, so it's time to start bringing in some information from the specification. As part of my MIDI file class, I'm going to add 2 enums. And I've primed the values of this enum with the words necessary to represent that event type. So in this case, we see things like voice note off and voice note on. So that's pressing a key and not pressing a key. We've got other controls which change the expression involved with the note. So pitch bend will slightly change the note whilst it's playing. We also have another type of event called system exclusive, and we'll be using that too today. System exclusive is not directly involved in producing sound, it's more about configuring the environment or the instrument. Note that it is the most significant nibble of this byte that really contains the information. The bottom 4 bits of the status event indicate which channel the MIDI event is being targeted at. So we only need to compare the top 4 bits of our status byte to see what the event means. And there's no real way around this, we're just going to need to successively check each permutation. So note off, note on, aftertouch, there we go, I've handled all of the event types. Now, fortunately for you guys today, I'm not going to go into detail for each and every single one of these, just the ones that I'm interested in for visualization. But we can't fully ignore them either. Don't forget we're reading sequentially from a file stream. So let's, for example, say we got a voice channel pressure event. We need to read the data associated with that event, or else our stream will become corrupted. I guess what I'm saying is, we still have to read in all of the information in a valid way, but for my visualization, I'm really only interested in capturing the voice note on and voice note off events.
Now it's time to talk about the third curiosity of the MIDI file format, and this certainly caused some confusion for me when I was attempting to reverse engineer all of this. It's called MIDI running status, and it's a way of compressing the data stream even further. Let's assume we wanted to send a sequence of MIDI events to an instrument. We would send the event time delta, the event data type, and the event data itself. And we would send that repeatedly over and over again. So if I wanted to press 8 keys simultaneously on a keyboard, I'd send delta, event ID, event data, delta, event ID, event data, etc. 8 times. But the event ID is the same for all of them, so that seems like 8 bytes I don't need to send. Recall that most MIDI data is in the range 0 to 127, therefore we only need 7 bits, and the most significant bit is superfluous again. Well, you may have noticed already that all of our event IDs are greater than 127, so that most significant bit indicates that the byte we've just read is an event ID. So if we read some time delta and then immediately read a byte that didn't have its most significant bit set, we know that actually what we've got is some active MIDI data. So which ID do we use? Well, we use the previous valid ID that was sent. So this means our stream of 8 events for the 8 keys being pressed would look more like the timecode delta, the event ID of the first one, and then the event data. And then simply it becomes time delta, data, etc., etc. So this is just another way the creators tried to optimize the bandwidth requirements.
And this caught me out at first because there are plenty of valid MIDI files out there that don't care about this optimization. But in order to be compliant and make sure we can read any MIDI file, we do need to care about it. So as soon as I've read the status byte from the stream, I'm going to check its value, because if we know that the most significant bit isn't set, then we've entered this MIDI running status mode. This requires us to keep track of the previous status byte that we read. And so if the byte doesn't have its most significant bit set, I'm going to set our current status to the previous status. But in order to get this far, I've had to read the byte from the stream. I've effectively just lost it. And so when it comes to reading the data of the individual events later on, I'm 1 byte out of place. Now I'm going to cheat a little bit here and simply instruct the stream to go backwards 1 byte. Just to recap, on a standard MIDI message we would have read the time delta and we read the status byte. We then interrogate that status byte to determine how we're going to read the data for that event. We've not done that bit yet. However, it's possible that a status byte simply isn't sent. But in order to know that, we've already needed to read as if it was a status byte, where in fact it was the first byte of the data of the current event. So this line here just makes sure that everything gets back in sequence. So how do we read the data? Well, let's assume a key is being pressed, voice note on. Well, rather lazily I'm going to cache the previous status and start parsing this data. Now, the bottom 4 bits of the status byte reflected which channel the event was being targeted at. So that's easy enough to extract. And for voice note on, there are 2 more bytes to read. The first byte indicates which note has been pressed, and the second byte indicates how hard the note was pressed. So the status byte told us that it was a voice note on event, and the specification says the next 2 bytes represent the ID and the velocity. And we'll see this is a common pattern throughout a lot of these events. So for voice note off, that's the key being released, we read the same 2 things. Now, even though for this video I don't care about what these other packets actually do, I do need to read the right amount of information from them because we're reading them from a stream. And it turns out that voice aftertouch is exactly the same. Voice control change is exactly the same. So the voice control change is the other dials and buttons on your MIDI instrument. However, program change isn't the same. It just requires us to read 1 additional byte, as does reading the channel pressure. Pitch bend is a little bit different again. It does require us to read 2 bytes, but this time they mean something different. And we'll come back to system exclusive in a little bit. I should also just add in here an else unrecognized status byte, just in case something has happened, there's corruption, or the MIDI file hasn't been rendered properly. So now we're reading in this stuff, what am I going to do with it? Well, my intention is to render the MIDI file on the screen in a way similar to what the MIDI editor I showed earlier is doing. So I don't really care too much about using this as some sort of MIDI processor, but I do care about translating the events I'm reading from the file into information that I can use in my application. I know potentially I'm going to have multiple tracks, so I'll create a structure called MIDI track, which I'm going to have a string for the name, a string for the instrument, and I'm also going to have 2 vectors. These vectors are going to store the events in 2 different ways. The first one, MIDI note, is just simply the key, the velocity, when it starts and how long it's going to be. So that will effectively be what I can draw on the screen. The other is going to be a MIDI event. It's sort of a cruder form of storing the MIDI information. And I'm only interested in notes being pressed, notes being released, and everything else I'm not bothered about. So as we now read through the file all of the different MIDI events, I'm going to add them to this MIDI track. And I'll store all of these tracks in my MIDI file class in a vector of MIDI tracks. At the start of our loop, we know we've got a new track, so I'm going to push a blank MIDI track into that vector. Let's take the voice note off event as an example. I've read in the relevant information. I'm now going to construct a MIDI event using that information, in this case note off, the note ID, the velocity and the time delta, and I'm going to push it into my vector of MIDI events for that particular track. I'll do something very similar for voice note on. However, here is another little quirk of the MIDI protocol. It turns out that any voice note on event where the velocity is 0 is actually going to be considered a note off event. So I will check what the note velocity is and then add to my vector events, well, the appropriate event. Now, as I've mentioned already, I don't particularly care about the other events, but I'm just going to push something to my vector for now. So far, so good, and reasonably quite simple. It would be great if MIDI files just contained this basic event information, but sadly they don't, and this now adds some complexity to what we need to read in, because we have to read in everything to make sure that all of the data we're reading is valid. And this complexity comes through the guise of these system exclusive events. Now, in the source code that accompanies this video in the GitHub, I've gone through these events in some detail. I'm not going to do that for this video, other than to look at one or two of them. All we care about for now is knowing how to read them properly. So I'm going to add another enum to my MIDI file class for all of the system event types, meta events in this case. And this contains all sorts of, well, meta information, so generic text, copyright, what is the name of a particular track, what is the name of a particular instrument, are there any lyrics associated with this? This is the kind of stuff that the editors will use in order to configure a project around a particular MIDI file. Instruments don't care about this sort of thing. There are some critical ones, however. Setting the tempo, setting the time signature, that sort of thing could be interpreted by the instrument to change its speed. System exclusive is a way of making the file format flexible enough to handle future changes. And so in the future we may have messages which are not defined by the specification. These messages will be guarded by these two status bytes. Meta messages, however, are defined in the specification, and these always have FF specified as the status byte. When we know that our MIDI event is a meta message, we're going to read in what type it is, and we're going to read in the length, that could be variable length, of the message. Then it's simply a case of just processing the type. Now I've just cut and paste all of these in, all of these different meta message types. I'm not going to go through them in detail, but we'll have a look at some of them. So once we've recognized that the type, for example, is the copyright information of the MIDI, and we've read in the length of the message, the specification says that this is going to be a string of that particular length. So we're just going to read in that string with our readString lambda function. The same applies to things like the track name. That's totally decided by the composer. I think it's quite interesting to read the track name in because we can visualize it later with the MIDI events. And believe it or not, that's that. Read the header, read how many track chunks there's going to be, then read each track chunk individually, read the track chunk header, and start parsing the events. The events all have a delta time, they all have a status, and they all have an event body. If the event happens to be a system exclusive event, then it could be anything that we want. That needs to be defined particularly for a specific system, or it's going to be one of these meta events, which is defined by the standard across all MIDI files. And that's it. So we can start to test our parser by loading up a MIDI file. And I'm going to do that in onUserCreate. I'm just going to load the MIDI file that I was playing earlier. You'll notice that in the meta events, I've outputted a lot of stuff to the console. So if I run the application, the Pixel Game Engine doesn't do anything, but if I click in the console window behind it, we can see what's been outputted. And there's been a whole bunch of tracks there. We've managed to determine the time signature and the tempo, 185 beats per minute, and we can see that each track that we've read in has a name associated with it, typically which instrument is going to be played. There's also been some stuff in there that shouldn't be there. And this is one of the final curiosities I've learned about MIDI files, is they contain all sorts of junk that doesn't necessarily adhere to any particularly known standard. So that's why we have to be careful about making sure that we do read everything that we need to read. Well, I'm satisfied that there is certainly MIDI data being loaded. But right now, our MIDI file class contains vectors per track, and those vectors contain MIDI events. I'm now going to convert these MIDI events into something I can visualize. Don't forget the MIDI event works with delta time. And delta time is a little bit tricky when you want to draw things in the future. So I'm going to convert the relevant MIDI events into discrete MIDI things that have happened. So I'm going to turn them into these MIDI notes. I know the key, I know the velocity, I know when it starts in real time, and how long that note is held for, i.e. my MIDI note doesn't care about on or off. Once I've finished parsing the MIDI file, I'm now going to do this conversion from events into something which is more useful to me. So I'm going to create a little auto for loop that goes through all of the tracks for this MIDI file. Tracks can be treated in isolation, they run in parallel to each other. So timing information doesn't happen across tracks. I'll create a variable called wall time, which is my real time value. And it's my intention here to look at all of the MIDI events as we go through time and reduce them into my MIDI note events. And this has a little bit of complexity because the MIDI event is far simpler. It's on or it's off. But my note is on with a duration. So I need to keep track of which notes are effectively being held down at any given time and when they are released. And I'll do this by creating just a quick temporary list of MIDI notes of my list of notes being processed. And now it's time to iterate through all of the events in my vector of events. We know where we are up to in real time simply by accumulating the delta of every event. Now the deltas could be 0, that's okay, real time hasn't progressed. That just means two things are happening at the same time. If the event is a note on, I'm going to add one of my MIDI notes to my list of notes being processed. The problem is I don't know what the duration of this note is until I find the corresponding MIDI note off event for that particular note. And I'm really sort of hacking this together. I'm sure there's far more effective ways. If the event happens to be a MIDI note off, I'm going to search my list of currently processed notes to see if it's the same key. And if that search yields something, that means this is a note off event for a key that's already being processed. I now know its duration. And so I can work out its duration by looking at the current wall time minus the note that we've found start time. And since this note is no longer being processed, it graduates to being put into my tracks vector of notes. And I can erase the note being processed from the list of notes being processed. Those of you really paying attention will have noticed in my MIDI type structure I've got two additional variables, max note and min note, and I've set them to 64. Potentially for a MIDI event there are 127 notes. This is very rare to see something going from 0 to 127, and if I was to visualize this I would have a lot of blank screen with just a small line of things happening in the middle of it. So I'm going to record what the maximum note pressed was and what the minimum note pressed was, and that way I can scale the height of my track visualization. And I'll make a check for that here. And this will allow me that when I'm visualizing the track, I don't need to draw lots of blank empty space above and below where really all the action is happening in the MIDI file. Let's quickly construct the visualization. First, I'm going to clear the whole screen to black, and I'll add to the class a 32-bit unsigned variable nTrackOffset. And what I'm going to do is use track offset to move us forwards and backwards through time. I'm also going to need some variables that tell me how to actually visualize what I'm seeing. So per column, so this is 1 pixel across, is going to represent 50 ticks in the MIDI domain. Now ticks we've not really talked about, but fundamentally it is the clock that is operating behind the scenes for the MIDI system. So when we talk about these delta times, I've sort of roughly mentioned milliseconds, they're actually in MIDI clock ticks. And these ticks can be converted into real time by looking at some of the meta messages that have come through the MIDI file. Fortunately, most systems have the same definition for ticks. It is important that the frequency of the MIDI clocks used across your system is the same. Not only does it keep your instruments synchronized, but it means that one instrument is playing stuff at the same speed as the other. I'm avoiding going into timing control directly by maintaining the idea that a tick is an arbitrary time duration specified by something in this system. So I'm just going to make sure everything is relative to the tick. So per pixel on the screen, I've got 50 ticks, and each note I'm going to display as being 2 pixels high. For each track in my MIDI system, I'm going to draw its contents. But I'm only going to do that if the track actually contains something. You'll quite often see in MIDI files that tracks contain additional information, such as composers and orchestras and musical notes and that sort of thing, stuff that we can't visualize. I'm only interested in notes on and notes off. Because we know the minimum and maximum note of a particular track, I know what the range is for that track. And so I'm going to draw a grey rectangle across the screen using the fillRect function, the same height as the range of that particular track. I'm also going to draw the name of that track too. I've just introduced this n offset y variable. We're going to need to change this as we draw the tracks, because each track is going to have a different height, and we're going to have several tracks going down the screen. Now it's time to draw the notes, and I'm not going to optimize this in the slightest. I'm just going to draw them all, even if we can't see the majority of them. Each note is going to be drawn as a filled rectangle. The x coordinate for the starting point of that rectangle we already know because we've extracted it from the event sequence. And I'm going to offset it by our track offset value, and don't forget that one column of pixels represents 50 ticks. So I need to divide this number by the 50 to effectively scale it in the x direction. The y position of the note is determined by where we're starting to draw the track on the screen and the key value of the note. That affects its height, so as the notes get higher, we want to see them moving up the screen. The width of the note we've already determined because it's the duration of the note divided by the time per column. And the note height is just a constant that we've specified, and I'll draw that as a little white rectangle. I'll just add in a couple of user controls so we can change the track offset manually with the left and right keys. And that's our complete onUserUpdate function. As you can see, there's not much to it, and that's because we took the time to change our MIDI events into notes, something that we can tangibly work with in our own framework. So let's take a look. So it's loaded up the MIDI file from before, and we can see we've got tracks going down the screen. Each grey rectangle is a track, and they're labelled with the name of that particular track. And inside the tracks we can see there's lots of notes, and if I press the left and right keys we can scroll forwards and backwards in time. So in a way it's very similar to the MIDI editor software we saw at the beginning.
Now this has been a bit of a roller coaster so far, and I'm really pleased that we've accurately visualised the contents of a MIDI file. But I'm feeling a little bit empty and underwhelmed. It's MIDI, we're meant to be hearing things, we're meant to be sort of making lots of strange noises. So I'm going to now just really quickly hack in something, and I'm sorry it's Windows specific, it's a total bodge, it's a complete hack. But what I'm going to do is take our notes, convert them back into MIDI events and send them to one of my synthesizers so we can hear it.
And this time I really do mean we're going to do this quickly because I'm not going to go into any details, but what I'm going to do is load the Windows Multimedia Library, which will allow me to access the MIDI drivers built into Windows. I've no doubt people out there will be able to come up with a Linux alternative. I've just added some additional variables to the main class that will maintain timing. The Windows Multimedia Library is considered a bit old hat now for real-time audio, but it's still fantastic for MIDI. In fact, it's very simple to just quickly open an instrument. In the onUserUpdate function, after we've drawn everything, I'm just going to throw in a quick test where we're going to be sensitive to the spacebar being pressed and released. The Windows library easily allows us to send a MIDI message to an instrument, and it's the same format that we've been working with already. Here we've got the status byte, here we've got the note, and here we've got the velocity. So when I press the spacebar, I'm setting a note to be on, and when I release the spacebar, I'm turning it off. So here you can see one of my synthesizers. If I press a key, beautiful. And I've connected my synthesizer to my computer via USB, and it will transfer MIDI information via the USB. So let me start my application, and we can see the MIDI track that's been drawn, but I press a key on my synthesizer, but I can also press my spacebar. So the spacebar is linked to my synthesizer via MIDI. Now, I'm not kidding when I say this is bodged code at its best. It violates all sorts of rules and principles. I do not recommend that you do anything this way. But it's just to allow us to prove a point. So what I'm effectively going to do is take our note sequence, convert it back into MIDI, and issue those events to my synthesizer. So let's take a listen. Now my synthesizer can only play one track at a time, So I've chosen track 1, which is sort of the lead string ensemble from before, and I'm going to play it. And hopefully you can hear that I can real-time manipulate the sound from my synthesizer. The MIDI file I've been working with is quite a simple one, so I want to try a slightly more complicated one. So let me just choose an appropriate patch on the synth, that one will do, and let's play this file. This time though I'm going to play both tracks simultaneously, so I have a small loop here, instead of just one track. Let's have a listen. And as we can see, it's quite happily loaded in absolutely every single MIDI note. There's an additional track at the top here that contains tempo change information, which I'm not using in my playback. But this is a very sophisticated MIDI, lots of different notes going on. It seems to have loaded it all and handles it quite well.
And so that's that. A quick and simple look at the MIDI file format. Now I like MIDI, I like sound, I like programming, and I think I'm going to merge it all together. You don't have to just use MIDI for instruments, it can be used as general purpose timing control too. And I know for a fact that there are certain firework displays and lighting shows which are completely coordinated by MIDI also. And that actually gives me an idea for a game, so I'll have a think about that. Anyway, if you've enjoyed this video, give me a big thumbs up, please have a think about subscribing. The source code will be available on the GitHub, and I'll see you next time. Take care.